In this lecture, let's write our very first kernel module. Here is an example of a kernel module, a Hello World kernel module. It looks like a normal user space C program, but we have to understand a lot of things here. So because we write kernel module according to some rules, because the kernel module is going to run in the kernel space. Let's understand this program step by step. Here we can divide this program into a couple of sections. There is a header section, there is your code section, and there is a registration section, and there is a module description section. Basically, these sections are part of a kernel module. Let's go through these sections one by one. First of all, let's explore the header section. Here you have to mention the appropriate kernel header for your kernel module. You can find all the kernel headers in kernel source tree in the path include Linux. That's a place where all the kernel headers are placed. In that location, you find a kernel header called module.h. Every kernel module should include this header file because it has got definition of various macros which you are going to use while writing a kernel module. Let's explore about what is the difference between kernel header versus user space header. For example, what you just saw here is a kernel header. So an example for a user level header may be stdio.h. That's a header file what you find in the standard C library. That's the user level header. This is a kernel header. Since you write a kernel module that is going to be executed in kernel space, you should be using kernel headers. Never include any user space library headers like C standard library header files. No user space library is linked to the kernel module during a kernel build procedure. For example, you don't link your kernel module code with a C standard library. You don't do that. That's the reason you should not use any user space headers while writing the kernel module. Most of the relevant kernel headers are placed in the Linux source tree at the path include Linux. Let's move forward. Now let's explore about the code section. Here your code is nothing but collection of couple of functions. This is a normal C function, but it looks weird because it has got some kernel related syntaxes. That is very easy to understand. I will explain that. But it does look like a normal C function. Basically, while writing a kernel module, we use two entry points. Here, the first function is called as module initialization entry point, or in short, I call it as module initialization function. And the second function is called as module cleanup entry point, or in short, I call it as module cleanup function. Initialization function and a cleanup function. You don't see a main function here, so there is no main function. We talk about entry points. This function is an initialization entry point, and this is a cleanup entry point. Inside the function, you can write any code. For example, here I am using some kernel printing services or printing APIs to print some data. So we'll explore about kernel's printf later. Let's move forward. Let's understand more about module initialization function, why it is required. First of all, this is a prototype of a module initialization function. It should return int, and function name you can give anything you want, your custom name, and it will not be taking any parameters, so input parameters are void. The module initialization function must return a value, 0 for success. Non-zero means module initialization failed. So the module will not get loaded into the kernel. This is an entry point to your module like main. We talk in terms of entry points. This function will get called during boot time in the case of static modules. In the case of dynamic modules, this function will get called during module insertion. That should be one module initialization entry point in the module. For example, if you compile this kernel module as a dynamic module, then this function will get called when you insert the module into the kernel using user-level programs such as insmod. Let's move forward. Let's explore more about module initialization function. What you do here, you do some initialization of devices, initialization of device private data structures. You request some memory dynamically for various kernel data structures and services. You request for allocation of major and minor numbers, device file creation, various things you do in this function. So all these things we are going to understand when we write a character driver in the upcoming lectures. Basically, you do initialization related things in this function because it's an entry point. It's like a main. Let's understand the complete syntax of this function. You have got static keyword there and you have got underscore init tag there. So what are those? We have to understand that. The module initialization function is module specific and should never be called from other modules of the kernel. Because it's an initialization function of a module, so why would other modules will call it? It is module specific. It should not provide any services or functionalities which may be requested by other modules. You should not give any services here which may be required from other modules. Hence, it makes sense to make this function private using static, though it is optional. Here, static keyword is actually optional, but as I said, this is module specific and it is private to module. Then it's good if you make this function as static function, right? Private to a file or private to a kernel module. That's the reason why we use static here, but it is optional. Let's move forward. I'll come to that init tag later. That is underscore init tag or a macro. So I'll come to that later. Let's understand module cleanup function. This is a prototype of module cleanup function. Return type is void. Function name can be anything. Your wish, you can give any name here. And it doesn't take any input parameters. This is also an entry point when module is removed. Since you cannot remove static modules, cleanup function will get called only in the case of dynamic modules when it is removed using user space commands such as rmmod. If you write a module and you are sure that it will always be statically linked with the kernel, then there is no need to implement this function. Even if your static module has a cleanup function, the kernel build system will remove it during the build process if there is an underscore exit marker or tag. What you do inside the cleanup function? Typically, you must do exact reverse operation what you had done in the module init function. Cleanup does undoing what init function has done. You free some memories which are requested in init function. You can also de-init some devices or leave the device in proper state. That's the job of cleanup function. Again, when we write some drivers, you will understand how to use this function. Basically, what you should remember here is for static modules, cleanup functions are not required if you are very much sure that it will always be linked statically to the Linux kernel. And if a module is dynamically loadable module, then a cleanup function gets called whenever the module is removed by using user level programs such as rmmod. In the next lecture, let's understand what exactly are these macros, that is underscore init and underscore exit. We'll understand whether it is really required or what's the advantage of having these macros or markers. I'll see you in the next lecture.